Hello, and welcome to part 2 of the Hobby Electronics Mega Channel presentation on flashing and lighting LEDs using multivibrator circuits. I'm Dylan Z, and in this, the last part of the series, I'll be taking you through building and stepping through an astable multivibrator circuit. This one, when powered on, oscillates between two states indefinitely, or for as long as the battery lasts. The duration of the two states is determined by two sets of timing resistors and capacitors. The main uses of an astable multivibrator circuit are oscillation, pulse width modulation, and generating clock pulses for digital ICs and other circuits. The circuit we'll be building today is a dramatically slowed down oscillator. We want it to alternate between its states slowly enough so that we can detect its changes in state visually with the LEDs. If you have not already, watch the first video of this series first. It's linked on screen for you. It's not absolutely required, but I do go over the components needed for this particular circuit, and we'll be combining the circuits at the end of this part, so it will be helpful to go through it first. As with any hobby electronics project, safety is number one. Though the voltages and currents we will be using are extremely low and pose no danger, aside from damaging components, I urge you to check the two websites shown on your screen for safety tips when working with electronics. The information there is very useful. Now let's go ahead and build this circuit. Let's start by placing two LEDs as shown. Remember to place the bulbs correctly, observing the proper polarity. As with all my tutorials, I will highlight in red the holes of the breadboard where components are to be placed. In cases where polarity is a concern, the holes will be highlighted in red for positive and blue for negative. Next, place the two 470 ohm resistors as displayed, followed by the two 47K ohm resistors. Now we'll place the 22 microfarad electrolytic capacitors, attending to the polarity as marked on screen. The transistors come next. I've marked clearly, as usual, the holes where the collector, emitter, and base pins for each transistor should be placed. Finally, once those have been placed, connect the negative side of the left capacitor to the base of the right transistor, and then the negative side of the right capacitor to the base of the left transistor. That's all there is to building this simple circuit. We're ready to connect your 9-volt battery to the circuit and watch it go. With the current resistor capacitor sizes, the LEDs should alternate blinking about once per second. Again, changing the sizes of these resistors and capacitors will result in different durations of the LEDs being lit. As we did with the monostable multivibrator circuit, now we'll step through the chain of events that occurs when power is applied to the circuit as displayed on the astable multivibrator schematic. I need to say before we begin this step through that it is not possible to tell which state the circuit will start in once power is connected. For the sake of argument, we will start with state 1 being the state where the left transistor is on and the right transistor is off. In reality, it could be the other way around, but it will always alternate between the two states. First, when power is applied, current flows through R1, through LED 1, lighting it, through Q1 to ground. CT1, the left timing capacitor, at this point is fully charged. Positive charge on the left plate of CT1 flows out of the capacitor through Q1 to ground. Negative charge on the right plate of CT1 sucks up all the current flow through RT1, the left timing resistor, ensuring Q2's base receives no current, thus keeping Q2 shut off. The negative charge on the right plate of CT1 is slowly increasing towards 0 volts, and will eventually become positive, as the left plate continues to release its electrons to Q1, attempting to stabilize the capacitor. Meanwhile, CT2, the right timing capacitor, is fully discharged, and Q2 remains off. With Q2 being off, electron flow through R2 collects on the right plate of CT2, charging it. While CT2's right plate is charging, its left plate is building up a negative charge, pushing even more current from RT2, the right timing resistor, through Q1, keeping it turned on. The change in state occurs at CT1, when its right plate, initially negative, has increased its charge, as its left plate has lost positive charge to Q1, to 0.6 volts. When this occurs, enough current passes by CT1 from RT1 to the base of Q2, turning it on. Many things occur now. Firstly, CT2's positive charge begins flowing through Q2's collector to ground. Current flows through R2, through LED2, lighting it, through Q2 to ground. As CT2's right plate charge decreases, its left plate charge will increase, pulling all current from RT2 and depriving Q1's base of any current, thus shutting off Q1. LED1 turns off as all current through R1 is now collecting on CT1's left plate, and it begins recharging. Meanwhile, CT1's right plate is building a negative charge, pushing all current from RT1 past it to Q2's base, keeping Q2 turned on. The next change in state occurs now at CT2, when its left plate charge has increased through 0 volts to 0.6 volts, allowing enough current past CT2 from RT2 to Q1's base, turning it on. The cycle then starts over at state 1, repeating itself indefinitely. I urge you to experiment with the values of the timing resistors and capacitors to see what results you get when various values are used. With the timing resistors being 47K ohms and the timing capacitors being 22 microfarads, your results should match what you're seeing on screen now. The practical applications of this circuit are bounded only by your imagination. You can use the Astable Multivibrator to operate a DC motor, changing the speed of the motor by introducing a variable resistor. Another idea is to use it to provide dimming functionality to a lighting system. In fact, one of the upcoming 555 timer series videos will address this very application. I promised early in this video that we would be combining these two circuits, the monostable multivibrator circuit from part 1 and this astable circuit. We're going to do that right now. On your screen, you can see the two circuits on the same breadboard, the monostable circuit on the bottom and the astable circuit on top. I have replaced the 10 microfarad electrolytic capacitor in the monostable circuit with a 220 microfarad electrolytic capacitor, thereby increasing its timed output pulse from 1.1 seconds to approximately 15 seconds. I have also removed the output LED and its resistor, and replaced it with a wire that feeds up to the astable circuit. I've added 2 transistors to the astable circuit that are wired so that they turn on when the button is pressed and the monostable circuit begins its timed pulse. This essentially grounds the astable circuit for the duration of that pulse, allowing its oscillation to occur. At the end of the monostable circuit's pulse, the transistors shut off and the astable circuit stops receiving current. The upshot of this is that when the button is pressed, the 2 LEDs will flash back and forth for about 15 seconds. This demonstrates how the two circuits can be used together in a practical application. I have not gone into detail regarding the 2 additional transistors, so try this out and see if you can configure the 2 circuits as I've done. If you get stuck or have any questions, please post them in the comments for this video, and I will reply. This two-part tutorial has been a precursor to an upcoming series of video tutorials designed to show off the features of the 555 timer, which handles monostable and astable circuits much more efficiently than the ones we have built here. Check those videos out. I assure you, you will not be disappointed. I hope you've enjoyed this two-part multivibrator series. As always, it's a pleasure to walk through building and explaining these circuits. Take the knowledge you've gained here and apply it in your own hobby electronics experiments. Subscribe to my channel if you haven't already, and feel free to leave comments or ask questions. Until next time, I'm Dylan Z. So long for now.